This one might have been on one of the practice problems that I put on the web. I'm not sure. I'm not sure what finals I put on the web, but there are some practice finals on the web, by the way. This is a long coaxial cable of length L, has a solid wire in the center, and then a conducting tube around it. The center one is charged plus Q. The outer one is charged the same, plus Q. So the question is, find the surface charge densities on the inner wire and the inner and outer surfaces of the outer wire, and find the electric field between the conductors. So in cross-section, it looks something like this. This has a total charge Q. Surface charge density, sigma, is Q divided by, of course, I needn't say, I hope, that if you put a Gaussian surface inside here, there's no electric field inside the conductor. Let me just leave it that way. There's no charge inside the conductor. It's all on the surface. All of Q is on the surface. So sigma 1 is Q divided by the surface area of 1. What's the surface area? Well, 2 pi R1 is the circumference, and the length is L. So that's the surface area of R1, or at R1, of the inner one. So this whole thing has Q on it. What is the inner? What is the inner surface of that tube? What's the charge on that? Negative Q. Charge on that is negative Q. Why did it end up that way? If I ever ask you why, well, suppose you put a Gaussian surface around that inside the conductor. You'd know there was no electric field, so no flux, so no charge enclosed. If that has Q, this other surface better have negative Q so that it cancels out and no charge is enclosed. So negative Q inside there, sigma 2, negative Q over A2, negative Q, 2 pi R2 L, surface charge density on the inner surface there. What about the outer surface? Well, the outer tube, the tube has charge plus Q. So if it's a negative charge on the inner surface, then there's 2Q on the outer surface, and you can continue on there. Electric field in between, just due to the charge enclosed. This is cylindrical. So I think that you'll find that the electric field drops off linearly with R in between the two, using Gauss's law. Yeah?
Wait, why is it 2Q not such?
Because the total charge on the tube is plus Q, the same as the charge on the inside. As same as the charge on the rod in the center. So if minus Q came to the inner side and the total charge is Q, then the inner surface and the outer surface charges have to add to Q. If the inner is minus Q, the outer has to be 2Q. Just because something tricky has been done by whoever wrote this, they made the outer one Q, the same charge as the inner one. And any other questions about this? I'm not going to go through Gauss's law for the cylinder because I think you can do that one. And I think you'll find that the electric field in here is linearly dependent on the radius because this is a cylinder.